Hello, everyone. My name is Burak Kantarci. I'm an associate professor at the University of Ottawa in the School of Electrical Engineering and Computer Science. I will be presenting our paper titled Participant Comfort Adaptation in Dependable Mobile Crowd Sensing Systems for IEEE Mobile Cloud 2020 conference. So this is the outline of the talk. I will give a brief introduction to mobile crowd sensing systems, and I will talk about the challenges and objectives of this work. And I will also present previous work that introduced some of the concepts that I will be talking to present this work, particularly on recruitment strategies. And then I will present our proposed user comfort adaptation model. And then I will be presenting and discussing the simulation results, and then I'll conclude my talk. So mobile crowd sensing, it's a cloud-inspired model to acquire sensory data from smart devices by taking advantage of the built-in sensors in those devices. So it's actually a viable tool to complement the existing dedicated sensing infrastructures. Just like what we see here, we collect the information from mobile phones instead of dedicating sensors, and then that information is uploaded to a cloud platform. So that's why this is a cloud-inspired model, because the providers here are providing their built-in sensors and their devices as a service to us. And of course, there might be some incentive models to reward these service providers, I mean the mobile phone users in this model. Okay, this actually brings several challenges and objectives here, objectives to address those challenges actually. Now, the first challenge is to ensure the trustworthiness of the data that's being acquired through mobile crowd sensing systems, because we can't avoid having adversaries or malicious users in the environments when we go with such a model. And on the other hand, we need to accommodate participants' preferences for their participation, because not everybody will be comfortable to grant access to all sorts of sensors in their mobile devices. So they won't be able to participate in all of the crowd sensing campaigns. So we need to also maintain trustworthiness while also accommodating user preferences. Now, the objective here is to build this work on a user comfort metric, which was introduced in our previous work. I'll talk about that. And then allow the users to adapt their comfort levels as the campaigns keep going. And at the same time, we also need to ensure the data trustworthiness. So we don't want to disrupt the campaigns dramatically, but we want to give the users flexibility to turn on and off some of their sensors depending on their context. So in our previous work, at the very beginning, we introduced a user selection, user recruitment scheme that was called selective and reputation-based recruitment, SRR. So in that work, participants were allowed to join some communities based on the reputations of those communities. As you can see here in this slide, there are two communities, group 1 and group 2, for this user to join. And the user is going to join one of these communities. So the selection criterion here is based on the reputations of these communities. But of course, the user has to watch a closeness metric here. So the selection factor here determines the target community to join. By joining a community, I mean selecting a mobile crowd sensing campaign and configuring the sensors accordingly. So Well, if your reputation is, let's say, 30%, you're not allowed to join a community that has 90% reputation. So that it has to be within a certain and predetermined closeness margin. So that was the whole idea behind selective and reputation-based recruitment. And this scheme shown the flexibility of selecting the tasks that are launched or submitted by the Crowdsensing platform. Now, I'm going to talk about the first set of performance metrics that we use in this work. The first performance metric is the platform utility. So it is actually the difference between the value of the total tasks that have been accomplished by the participants and the rewards delivered to the users. So that's the utility of the platform. And there's also user utility. It's average user utility, actually. So that's the rewards received from the platform minus the sensing costs, which we call the bids for these users. Now, of course, not all of the users are recruited in all campaigns, so we have to average it by the number of winners. Winners are the selected users per campaign. So this is the average user utility per mobile crowdsensing campaign. That's the difference between the total rewards and the total bids. There's also another important metric here we use, which is the disinformation ratio. So this denotes the ratio of the tasks that are being attacked by the malicious users. So if a malicious user is publishing fake sensed data, well, this is actually a disinformation. So the amount of tasks that have been infected by malicious users are called the disinformation or disinformed tasks. So these are the metrics that we care for. Now, while caring for those metrics, what we proposed recently was the reputation and comfort level aware participant selection. So this was presented in IEEE Symposium on Computers and Communications 2019. So shortly we called the scheme RA CLAPS. So this is also adopting a reputation-based recruitment. So if a user has been detected to be cooperative, and as the user keeps being cooperative, the reputation of that user keeps increasing. So it depends on how the reported data is consistent with the rest of the recruited community. So that's how reputation is formulated in these campaigns. But in addition to reputation, we introduced a comfort awareness metric here. So the users or participants are allowed to switch off some of the sensors depending on their comfort level. So not all of the users will be comfortable to share all of their sensors in this environment. So at the beginning, we expect all of the users to advertise a pre-modified sensor set before they join a crowdsensing campaign. So in this particular work in Mobile Cloud 2020, we develop an adaptive version of this. So, and we allow the users to adaptively determine their comfort levels and adaptively switch their sensors on and off depending on their context. And that's why we call this adaptive RA CLAPS. Now, in the next slide, I'll talk about our previous proposal, which is RA CLAPS. And then after that, I'll present what adaptive RA CLAPS brings on top of RA CLAPS. Now, this is our previous proposal. As you can see here, we have a user that has a high comfort level requirement. So the user does not grant access to their camera or microphone, as you can see here. So only GPS accelerometer and light sensor. So this is actually just an arbitrarily selected set of sensors for illustrative purposes. And we have a moderate comfort level user here. So the user does not feel comfortable to grant access to their camera, but microphone is available. And we have a zero comfort level user here. The zero comfort level user grants access to all of the sensors, as you can see. But of course, since we use some incentives to recruit these users, it is very likely that the zero comfort level user is going to be rewarded more than the high comfort level or moderate comfort level users, because the user is providing more data in comparison to the high comfort or moderate comfort level users. Now, our benchmark here is the zero comfort level based recruitment, but it also still cares for reputation aware recruitment of the users. So here, this is the user comfort aware recruitment. So this is what RA CLAPS brings to the picture. And our benchmark is the non-selective reputation-based user recruitment. And we will be using the short form of NSR in our performance results, as you will see in the next slides. Now, what we are presenting or what we are developing on top of this RA CLAPS framework is the adaptive RA CLAPS, as you can see here. Now, there are various criteria to turn these sensors on and off. As you can see here, we have this user, for instance, that does not give access to the camera. And we have this user that has high comfort level requirements, so that doesn't give access to the camera or the microphone. But depending on the context and their location, their requirements and needs can change. Now, what I can say here for this user is, okay, let's go back. Now the user grants access to all of the sensors, as you can see here. And the criteria is giving access to all of the sensors, but the microphone. So again, just for illustrative purposes. And if you look at this user, so initially, the user had a high comfort level requirement because it did not give access to their camera or microphone. Now, after some time, after changing the context, the user grants access to their microphone, as you can see here, but only camera is not being granted access. So they can adapt their comfort levels depending on their contexts. This is what the adaptive RA CLAPS user recruitment framework brings and introduces on top of what we earlier introduced and presented. All right. Now, there are some certain reliability levels here for the users. So this is a function of the user's reputation or the participant's reputation, and it is comparison to a predetermined threshold. Well, if the user's threshold exceeds, if the user's reputation exceeds a certain threshold, which we call the high reputation threshold, well, the user is in the high reliability level. If the user's reputation is between the high reputation threshold and the moderate reputation threshold, the user is in the moderate reliability level. If the user's reputation is between the moderate threshold and there's a naive threshold, this naive threshold is the initial reputation that is assigned to all of the users as they join the mobile crowdsensing campaigns. If the user's reputation is in between this, well, we call this the naive reliability level. And there's also a low reliability level. If the user's reputation drops below the naive threshold, then it's the low reliability level. So this is what we can say about the relation between the reliability levels and the access to the sensors. Now, as you can see here in the high reliability level, there's access to GPS, accelerometer, and the light sensor. So there's no access to camera and microphone. For the moderate reliability level, we have the camera turned off and the rest are turned on. In the naive reliability level, well, this is another reliability level we define here. Only microphone is not granted access, but the rest are turned on. Low reliability level, well, this is giving access to all of the sensors. Now, why are we making this assumption? Well, as a user's reputation falls below a certain threshold, the likelihood for that user being recruited again in the next campaign also drops down. So the only way for that user to build reputation is to provide more data and provide more trustworthy data. So if a user's reputation falls below that naive threshold, we expect that user to be more cooperative, assuming that the user is aiming to be cooperative. Even for malicious users, at some point, they need to increase their reputation. So assuming that if the user's reputation is below the naive threshold, well, we expect them to turn on all of the sensors to join the crowdsensing campaigns more aggressively. But if the users build more reputation, well, there's more flexibility for them. As you can see here, for the high reputation users, they can turn off their cameras and microphones. So this allows us to define adaptive comfort levels for the users, also considering their reputation. But there's also another thing. After every predetermined number of iterations, by iteration I mean campaigns, we ask all of the users to turn on all of the available sensors. So this configuration has to be reset after every certain number of iterations. This is to ensure that the platform utility is not being significantly degraded. So remember, I had introduced some performance metrics before. And those metrics were the platform utility, an average user utility, and disinformation ratio. So those are the conventional metrics that we've been using. Now, there are some additional performance metrics that we need to consider here. First one is the total energy consumption. So this is the maximum possible energy consumed by the total selected users. And of course, here we need to know whether or not a user has bid for a particular task in a particular campaign. So this binary value will indicate that. And of course, the energy value associated to the sensors that are currently on in that mobile device, right? And if the GPS is always on, well, we need to also include the GPS energy consumption as well. There's also a discomfort component. So this is the average weight of the sensors that are switched on by the selected users. And we need to get an average of the discomfort value by averaging this over the entire campaigns that this user has participated. So the discomfort component, as you can see, it's the average weight of these sensors. We assign a weight to these, a discomfort weight to each of these sensors. And based on that, the discomfort component is obtained. So this was introduced in our previous work in detail. So the discomfort component will be also used here to evaluate the overall efficiency of the system. Now, to evaluate our proposal, this is a summary of our simulation settings. So we have 1,000 users and we have tasks arriving at the crowdsensing environments varying from 20 to 100 tasks per minute. And it is assumed that a participant who is joining for the first time is assigned an initial reputation of 70%. This is actually based on the previous studies. So none of these numbers are arbitrarily selected. So all of them have been selected based on some previous studies. And for the thresholds here, these are determined empirically. Maybe I can say a few words about that. The high, moderate, and naive thresholds, remember the reliability levels I presented in the previous slides. So these are selected empirically. So 95%, 80%, and 70%. So if the user has a reputation at 95% and above, we allow the user, or the user has sufficient reputation and sufficient income, so the user can turn off the camera and microphone and switch to a high comfort level. So if the user is between 80% and 95%, that's the moderate level. So one additional sensor is being turned on here, and in the naive level, reliability level, the user, remember, aims to increase the reputation by joining more campaigns. So the camera is being turned on, but the microphone is being switched off. And if it is, of course, below 70%, remember, it is actually the low reputation and low reliability level. So the user aims to improve their reputation. So they switch on all of the sensors in their mobile devices to increase their likelihood of being selected in the upcoming campaigns. Now let's see the simulation results in the next few slides. So this is the platform utility. As we see here, so NSR is the non-selective reputation-based recruitment. And the second one is our previous proposal. So that's the RA collapse. Again, it's the comfort-based selection of the users, but there's no adaptation here. And this is what we propose. The light gray bars are our proposal here. So the platform utility, as expected, it is slightly decreased because we allow people to switch their sensors off. And of course, since they're allowed to switch some of their sensors, we give them the choice to reduce their own utility. That's based on their own choice. For the rewards to the malicious users, there's not a significant improvement here. And when we check the disinformation ratio, again, we don't see any significant increase in the system when compared to the non-selective reputation-based recruitment of the users. So we are not disrupting the system by introducing this comfort parameter here, and by allowing the users to adapt their comfort levels based on their contexts. So this is the idea. Now let's see further metrics here. So the user comfort component, as you can see here, we have the comfort gain metric here. So comfort gain metric is actually a function of the difference between the maximum discomfort and the obtained discomfort divided by the maximum discomfort. So this is the comfort gain parameter defined here. And when we compare the proposed adaptive approach to the static version, which was presented earlier, RA collapse, as we can see here, the comfort gain with respect to the benchmark is significantly increasing. And if the number of tasks per minute is equal to 100, which is actually an aggressive campaign, we can double the comfort gain, as we can see here. And also, when the tasks are arriving at a lighter load, the comfort gain, the improvement in the comfort gain when compared to the static version is also significant. For the overall efficiency, what do we mean by efficiency? First, maybe I should talk about that. Well, the efficiency of the system is an evaluation of this system based on the change in the utilities from the user standpoint and the platform standpoint, and also the change the improvement in the user's comfort. So we are trying to make a compromise between the utility of the platform and the user, as well as the comfort levels of the users. Now, this part, these two columns, these are already presented, these have been presented in the previous results. So we know that the platform utility and the user utility is being slightly reduced because we allow people to turn off their sensors and to select a new configuration for them based on their comfort level, and we allow them to modify that configuration based on their context. So how does that affect the user's comfort level, and how is the efficiency in terms of the comfort? So this is actually improvement in user comfort with respect to the benchmark scheme. So if we go with the static approach, this is the improvement over the benchmark approach, benchmark scheme, which is NSR, non-selective reputation-based recruitment. And if we go with the adaptive version, we allow the users to improve their sensor configuration depending on their context. And that's why the user comfort component is improving here. So the efficiency in terms of the user comfort is significantly improving compared to the static version of this framework. Now, the overall efficiency of the system, as I said, it's actually a weighted function of the changes in the utilities and the changes in the user comfort components. That's how it is defined in the paper. So as we can see here, the overall efficiency of the system is significantly higher when compared to the benchmark mechanism, benchmark recruitment mechanism, when we have the user comfort levels adapted based on their contexts and based on the changes in their reputation. So to conclude, our proposed adaptive comfort-aware user recruitment scheme significantly improves the user comfort level. So it is, of course, an improvement over the user selectiveness approach that had been presented earlier at the very beginning. So this was previously shown. Now, if we adaptively adjust the user comfort levels by adaptively modifying the set of sensors in these participant devices, this will improve the user comfort and, of course, at the same time, the overall efficiency of the system, which is making a compromise between the user utility, platform utility, and the user comfort level. So this, at the same time, ensures to maintain a certain data transportedness level in the mobile crowd sensing campaigns. You may remember the bar charts that I presented related to the disinformation ratio and the rewards made to the malicious users. So we are not remarkably increasing the disinformation ratio nor the rewards made to the malicious users. So the transportedness level is still being maintained at a certain level. And we're not making any dramatic performance degradation in the entire system, so there's not too much disruption. So we can maintain a certain level of user comfort if we adopt this adaptive array collapse mechanism while recruiting the users in mobile crowd sensing campaigns. Well, thank you very much for listening.